Among the vast array of stars, WOHG 64, often dubbed the behemoth star, stands out as an extraordinary anomaly. This red supergiant, located in the Large Magellanic Cloud, is so immense that, if placed at the center of our solar system, its outer layers would extend beyond Jupiter's orbit. Its sheer size and luminosity challenge our understanding of stellar physics, pushing the boundaries of what we consider possible in star formation and evolution. As we delve into the science and implications surrounding this colossal star, we uncover a universe far more violent, beautiful, and bizarre than previously imagined. A universe of fire. What makes a star a giant? We can only see tiny bits of light when we look up at the stars, but behind those flashes are raging circles of nuclear wrath, cosmic fires that make life possible, bend time with their gravity, and light up whole galaxies. Still, not every star is the same. A lot of them are nice, like our Sun. Others are gigantic, growing so big it's hard to imagine, and their flames are so bright they could swallow worlds whole and still want more. But what does a star giant look like? In stellar terms, the word giant isn't just hyperbole. It's a specific stage in a star's life. After a star exhausts the hydrogen in its core, it begins to burn heavier elements in a shell around that core. The outward pressure from this new phase of fusion causes the outer layers of the star to balloon outward. As a result, it becomes a red giant, a swollen version of its former self. For stars far more massive than the Sun, this process leads to something even more extreme: the red supergiant, or in rare cases, a hypergiant, a creature so vast that it could eclipse entire planetary systems. But how do we measure such enormous objects? Astronomers use units that stretch the imagination. The Sun, for instance, has a radius of about 696,000 kilometers. A red supergiant like Betelgeuse has a radius up to 900 times larger than the Sun. That means it could easily reach beyond the orbit of Mars if placed at the center of our solar system. But even Betelgeuse isn't the biggest. Enter WOHG 64, the behemoth star, an absolute leviathan, with a radius estimated to be up to 1,540 times that of the Sun. That would extend beyond Jupiter's orbit. Size, though, is only one dimension of a star's terror. Brightness, or luminosity, is another. Luminosity is the total amount of energy a star emits per second. Our Sun is a stable middleweight, producing enough energy to support life on Earth. But giants like the behemoth star produce hundreds of thousands of times more light and heat. They burn fast, they burn bright, and they die spectacularly. The most massive stars are often found in distant, irregular galaxies, like the Large Magellanic Cloud, where metallicity, the abundance of elements heavier than hydrogen and helium, is lower. This strange chemistry enables stars to grow far larger before shedding mass. These are stellar nurseries of extremes, where monsters are born and physics is tested to its limits. Being big is both good and bad in the universe. The life of a star is shorter the bigger it is. It goes through its fuel at a very fast rate because the pressure in its heart is so high. It only lives for a few million years, while the Sun lives for 10 billion years. There are no gentle old gods in the sky. These are raging giants living on borrowed time. The birth of colossal stars in strange galaxies. Stars that are very bright don't just appear out of nowhere. They form in places that are so rare and harsh that the rules for how stars form seem to be pushed to their limits. These huge galaxies like the Behemoth star, Stephenson 2, 18 and UY Scuti are not related to our Milky Way. Instead, a lot of them are born in strange places in the galaxy, like satellite galaxies or groups with strange chemical makeups, and a lot of violent starburst activity. Before we can understand how scary the power of the biggest stars is, we need to know where and how they are born. Metallicity, or the amount of elements heavier than hydrogen and helium, is a big part of how massive stars grow. Astrophysicists use the word metals to describe things like carbon, oxygen, and iron. which were all formed in the cores of older stars. The less metallicity there is, the easier it is for a gas cloud to collapse and turn into a huge star. That's because metals help get rid of heat, which makes the cloud break up and make smaller stars. In places with few metals, like some parts of the Large Magellanic Cloud, LMC, the gas clouds keep more of their heat, which lets them collapse into a few very large stars instead of many smaller ones. These environments are breeding grounds for massive star clusters, which can contain hundreds or thousands of stars born nearly simultaneously. In such chaos, some stars quickly consume the dense gas around them, ballooning into giants. It's a process of cosmic cannibalism, where the stars that form first, or in the densest spots, monopolize resources. These privileged stars become the supergiants, the hypergiants, the monsters of astronomy. But it's not just about location. Turbulence and rotation within gas clouds play a crucial role. Turbulent motion can compress some regions of a cloud enough to form extremely massive stars. And when those gas clouds rotate just right, they can funnel material into the center with incredible efficiency. If gravity wins out over internal pressure, a single star can grow dozens or even hundreds of times the mass of the Sun before it ignites fully. There's also a strange cosmic paradox at play here. Big stars are harder to make, but they rule their surroundings. Their strong radiation shapes clouds close by, starting new waves of star formation, or if it's too strong, stopping other stars from forming at all. It's like a cosmic queen who steals all the attention and doesn't let anyone else shine. One of the most amazing facts is that it may have been much easier for the biggest stars to form in the beginning of the universe. When galaxies were young and full of pure hydrogen and helium, the conditions were perfect for population 3 stars to form. These are thought to be the first generation of stars, and could have been hundreds or even thousands of times heavier than the Sun. We've never seen them directly, but their offspring, like the behemoth star, may be far-away reminders of that chaos from long ago. The Large Magellanic Cloud, a cradle for titans. If the Milky Way is the grand center of our cosmic neighborhood, then its neighboring galaxy, the Large Magellanic Cloud, is the wild border. This close dwarf galaxy is rough and uneven, and it's full of raw star-forming power. Despite its small size, it is home to some of the biggest, brightest and strangest stars ever found, such as the behemoth star. It looks like a contradiction, a galaxy with a small mass, but a big strategy to produce stars. Located about 163,000 light-years from Earth, the Large Magellanic Cloud, LMC, orbits the Milky Way like a loyal companion with a secret weapon. Despite being just 1/10 the mass of our galaxy, the LMC has earned a reputation as a stellar nursery, producing more high-mass stars per unit of gas than the Milky Way. It's a galactic forge, burning bright with clusters and nebulae like 30 Doradus, better known as the Tarantula Nebula, one of the most active star-forming regions in the local group. So what makes the LMC so special? It comes down to chemistry and chaos. The LMC has lower metallicity than the Milky Way, meaning its gas is poorer in elements heavier than helium. In star formation, this is a big deal. Metals help gas clouds cool and fragment, typically resulting in many smaller stars. But in the metal-poor LMC, the gas stays warmer and collapses more easily into fewer, more massive stars. It's a galaxy that doesn't favor balance, it favors extremes. This is the perfect place for large babies, like the behemoth star, to be born. This star is deep in the LMC and is covered in a thick layer of dust that makes it hard to see even with infrared instruments. But it is one of the biggest and brightest red supergiants we've ever found, with a diameter more than 1,500 times that of the Sun and a light 280,000 times that of the Sun. It's not just big, it is barely hanging on, releasing its upper layers in a steady exhale like a star. The LMC has long served as a cosmic laboratory for astronomers to test theories of stellar evolution, especially at the massive end of the scale. Because of its proximity and clarity, there's less dust between it and us than in many parts of our own galaxy. The LMC allows telescopes like the Hubble and the Very Large Telescope to peer into the heart of star clusters and nebulae, capturing massive stars at every stage of life, from newborn blue giants to dying red supergiants. What's even more interesting is how exchanges with the Milky Way may have made it more active. Our galaxy's tides could be pushing gas in the LMC together, which could cause bursts of star formation. Some scientists even think that our two galaxies will crash into each other billions of years from now. It would be like today's fireworks, with stars shooting off like sparks. The LMC shows us a bit of a different time in the history of the universe. The galaxy's chaotic structure, gas that is low in metals, and energetic star nurseries are a lot like the early galaxies where the first big stars were formed. It teaches us more than just about stars like the Behemoth star. It teaches us how structure, complexity, and drama in the universe came to be. The Large Magellanic Cloud is more than just a small galaxy next door. We're looking into the primordial forge, a furnace of stars where size doesn't matter. Red supergiants versus hypergiants. What's the difference? At first view, red supergiants and hypergiants might look like the same kind of space monster. They are both very big, burn nuclear fuel very quickly, and are doomed to end in disaster. There is a small but important difference between hypergiants and other stars. Hypergiants aren't just bigger. They're breaking the rules of physics all the time. A red supergiant is a massive star that has evolved past the main sequence, swelling in size as it burns heavier elements in its core. These stars are generally between 10 to 40 times the mass of the Sun and can reach hundreds, even over 1,000 times the Sun's radius. Betelgeuse is the classic example, a bloated, aging giant nearing the end of its life. It's big, it's red, it's unstable, but within the bounds of what we expect from stellar evolution. Now enter the hypergiant. These are not just larger, though many are. They are defined by something more intense: extreme instability and loss of mass. Hypergiants, especially the yellow and red varieties, are stars that exist in a very narrow, dangerous window of stellar evolution. They burn fuel so rapidly and expand so violently that their outer layers are constantly being ejected into space. It's not just expansion, it's chaos on a cosmic scale. The Behemoth star fits into this picture not just because of its enormous size, more than 1,500 times the radius of the Sun, but because of its behavior. It has a massive dust envelope that extends nearly a light-year from its surface. That alone indicates extreme mass loss, a key signature of hypergiant status. Some astronomers debate whether to label the Behemoth star a hypergiant outright, but its spectral lines, mass loss rate, and unstable structure place it teetering on the edge of that definition. It is thought that there are only a few dozen hypergiants in our galaxy. Why? Because stars are only in this hypergiant phase for a very short time, often only tens of thousands of years, a blink in the grand scheme of things. They are transitional events, like pictures of stars breaking apart before their unavoidable end. Collapse, explosion, and change. What sets hypergiants apart spectroscopically is also fascinating. They exhibit broad emission lines and spectral anomalies, which suggest turbulence, shock waves, and powerful stellar winds. These are not peaceful giants. They are roaring furnaces under pressure, throwing off vast amounts of material in chaotic bursts. Their limits on brightness are another important difference. Most red supergiants are below the Eddington limit, which is the place where the pull of radiation equals the pull of gravity. Hypergiants, on the other hand, get close to or go over this limit, which is why they can't keep their atmospheres. The hypergiant state is like a bubble that is so blown up that even the smallest touch can cause it to burst. So while red supergiants are massive and majestic, hypergiants are unstable, short-lived, and mythic in scale. They are stars burning the candle at both ends, reaching for a cosmic crescendo that promises either a spectacular supernova or a direct plunge into black hole oblivion. Meet the Behemoth star, the beast in the cloud. If the universe had a hall of fame for cosmic titans, the Behemoth star would tower above them all, a bloated, burning beast of a star lurking not in our own galaxy, but in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. This monster is so big, so luminous, and so wrapped in mystery that it forces astronomers to rethink what stars are capable of. First discovered in the 1970s by astronomers Westerlund, Olander, and Hedin, whose initials gave the star its name, the behemoth star quickly stood out for its sheer scale. Estimates place its radius at around 1,500 times that of the Sun, meaning if it replaced our solar system's star, its surface would engulf Mercury, Venus, Earth, Mars, and stretch close to Jupiter's orbit. The scale is mind-melting. Picture the Sun as a tennis ball. The behemoth star would be a sphere the size of a football stadium. But the behemoth star isn't just big. It's also one of the most luminous stars we've ever found, pumping out roughly 280,000 times more light than the Sun. And yet, ironically, it's shrouded in darkness, ensnared in a dense, donut-shaped dust envelope that masks much of its radiance. This thick veil of stellar ash and expelled gas makes the star difficult to observe directly, but also hints at something far more fascinating. A star in the middle of self-destruction. It's not just a cloudy halo. The material that the behemoth star is throwing out is almost a light year across. It's like a death shroud moving slowly away, pushed away by strong star winds and unstable outer layers. This circle suggests that the star is rapidly losing its mass. This is a common behavior for stars that are getting close to the end of their lives and burning through their fuel at a rate that can't be maintained. And then there's the temperature. Despite its fiery power, the behemoth star is surprisingly cool for a star, with surface temperatures of just 3,000 to 3,400 Kelvin, cool enough to classify it as a red supergiant. Yet even among red supergiants, this one is an outlier. It sits near, or perhaps beyond, a theoretical limit called the Hayashi limit, a boundary in stellar physics that tells us a star of a certain mass shouldn't be able to remain stable at such low temperatures and large sizes. The behemoth star is defying that rule, which has left astronomers scratching their heads. We're still not sure if the behemoth star is a single star or a system with two stars. It's hard to tell if it has a friend because of the dust and the distance. Some ideas say that a bright blue and hot O-type star could be hiding just out of sight. If this is true, the behemoth star would be a binary star system. This could help explain why it has lost so much mass through collisions or reactions with the tides. But as of now, no partner has been announced for sure. Another interesting thing is that the behemoth star is in the Large Magellanic Cloud. This galaxy is known for having strange, huge stars. This might be because it has a different chemical makeup than the Milky Way, with less metal in it. That could mean that stars in the LMC change in different ways, get bigger, or die in more dramatic ways. The behemoth star might be the perfect example of this kind of strange growth. It is a star that was born in a place that lets it grow much bigger than we'd normally expect. A star, 1,500 times the Sun's size. Understanding scale. Numbers don't always show how unbelievable something is. It sounds cool when scientists say that the behemoth star is 1,500 times the diameter of our Sun. But what does that really mean? How can we understand such a huge unknown thing in a way that feels real, even if only for a moment? Let's begin with something small. The diameter of our Sun is about 696,000 kilometers. If you multiply that number by 1,500, you get a radius of more than 1 billion kilometers. This is such a huge sphere that it would go far beyond Jupiter's orbit if it were put in the middle of our solar system. No more Mercury, Venus, Earth, or Mars. Jupiter's moons? Toast. The upper rings of the Sun would get so big that they would swallow up the whole inner solar system. Still hard to picture? Imagine a standard passenger jet flying around the Sun's equator. It would take just over 6 months to complete the trip at cruising speed. For the behemoth star? The same journey would take over 75 years, one lap around a single star. The scale also warps our understanding of mass and gravity. The behemoth star is massive, but not proportionally so. While it's more than 20 times the mass of the Sun, its vast size means the material making up this star is incredibly diffuse. Its outer layers are like stellar fog, so spread out they're barely holding together under the star's gravity. You could fly a spaceship through the outer regions of the behemoth star and encounter less resistance than you would driving through Earth's atmosphere. Not only is this construction interesting, it's also dangerous. It is more likely for a star to collapse as it gets bigger. The behemoth star is also living on the edge. There is a limit called the Hayashi limit that tells us if a star with a certain mass can stay stable at a low temperature and a high radius. If you cross that line, the star starts to crumple in on itself or throw mass outward, sometimes very forcefully. The area around it is also affected by its size. Even though the behemoth star is pretty cool, it gives off a huge amount of energy because it has a huge surface area. That much energy changes its surroundings by heating up cosmic dust, moving away nearby matter, and maybe even changing how other stars form. It is a bully in every way. It shapes its part of the world just by being there. A scary thing about this size is that it might not be the biggest one ever. Some red hypergiant stars like Stephenson 2, 18, UI Scuti and others may be as big as or even bigger than the behemoth star. But from what we can tell right now, the behemoth star is one of the biggest by volume. Its dusty hood makes it hard to get exact measures. That could be part of the magic. Not only is the behemoth star huge, it's also hard to find. This star is so big that it's hard to understand, so far away that it's hard to see, and so unique that it's hard to explain. It's not just science that helps us understand its size. It's a way to change our ideas about what's possible in the universe. If the behemoth star replaced our Sun, solar system devoured. Think about what it would be like to discover tomorrow that the behemoth star had supplanted our Sun. It happened all of a sudden, with no notice and no time to get ready. There won't be a fiery morning to meet us. There would be no sunrise at all. Earth and the worlds nearby would already be nothing but smoke. The behemoth star's estimated radius is around 1,500 times that of the Sun, about 1 billion kilometers. That's far enough to completely engulf not only Mercury, Venus, Earth and Mars, but also Jupiter, the gas giant more than 5 times farther from the Sun than Earth. The entire inner solar system would be erased in an instant. The star's outer atmosphere would stretch close to Saturn's orbit, turning once familiar planetary highways into seething, turbulent plasma. But it's not just the size that spells doom, it's the heat and the radiation. The behemoth star emits over 280,000 times more light than our Sun. If, somehow, a planet survived the initial engulfment and remained in orbit just beyond the star's new radius, the conditions would be unimaginable. Surface temperatures would soar to thousands of degrees Celsius. The atmosphere would be stripped. The oceans would boil into space. Radiation levels would spike to lethal levels in moments. The gravitational disruption would also be catastrophic. The mass of the behemoth star, though only around 2025 solar masses, would still be enough to drastically alter the orbital mechanics of every planet, moon and object in the solar system. Planetary orbits would be stretched, bent or even snapped. The Kuiper belt would be flung outward. The Oort cloud might be scattered into deep space. Everything held in the delicate balance of the Sun's gravity would now respond to a new, more aggressive force. And then there's the solar wind, or in this case, stellar wind on steroids. Red supergiants like the behemoth star shed mass constantly in the form of stellar winds, blowing off their outer layers at high speeds. The solar system, once a quiet neighborhood, would become a maelstrom of charged particles and dust. Space weather would turn deadly. Satellites and spacecraft would be shredded or melted. Space travel, out of the question. Not only would we have to deal with loss, but also change. Our solar system's once familiar structure would be changed by the gravity and radiative pull of a dying behemoth. The livable zone, that safe area where water stays drinkable, would be pushed to the very edges of the solar system, maybe even further. Planets near Uranus and Neptune could turn into very hot infernos. When moons are frozen, they could boil and burst. And yet, even with all this chaos, the behemoth star would not remain stable for long. Stars this large live fast and die young. In cosmic terms, this monster is on borrowed time, ready to collapse, explode, or shed its layers in spectacular fashion. Its presence in the solar system wouldn't just end life as we know it. It would set the stage for an entirely new kind of solar system, one filled with dust, debris, and the lingering echo of a star too big to last. A light in the darkness, 280,000 times more luminous than the Sun. Not only is the behemoth star much bigger than our Sun, it also shines brighter in every way that can be measured. With an estimated brightness about 280,000 times that of the Sun, it is one of the brightest stars that people have ever found. That being said, what does that number really mean in real life? The amount of energy a star gives off every second is called its luminosity. With a brightness of about 3.8 x 10 watts, the Sun isn't bad either. It helps keep the Earth's temperature, weather, and respiration going from about 150 million kilometers away. Do that again with 280,000. That's 1.064 x 103 watts, which is a number that is so huge it's hard to understand. It's not just a flame versus a bonfire. It's like comparing a matchstick to the explosion of a planet. This blinding brightness isn't just a curious data point. It dramatically affects the space around it. The radiation pressure alone is enough to blast the star's own material into space, creating powerful stellar winds and vast shells of dust. And while most of the behemoth star's light is emitted in the infrared and visible spectrums, its sheer intensity means it would be detectable across vast intergalactic distances, if not for the thick cloud of dust partially obscuring it from view. Much of what we know about the behemoth star comes not from direct optical observation, but through infrared telescopes like those used by the Very Large Telescope in Chile. These instruments can peer through the dust to read the star's spectral fingerprints, telling us how much energy it releases, what elements are in its atmosphere, and how rapidly it's shedding its outer layers. This unbelievably bright light also points to a star in trouble. The behemoth star is pretty much at the end of its useful life. Stars this bright use up their fuel at unsustainable rates. Our Sun still has about 5 billion years to go, but the behemoth star will only be around for millions of years, which is a blink in the grand scheme of things. Its huge amount of energy output shows how important this is. It's like a dangerous nuclear engine going at full speed, knowing its time is running out. And that brightness, that huge cosmic light bulb, doesn't just shine. It changes things. It makes the place clean. Chemicals are broken up by it. If an unlucky planet happened to circle close enough, it would be hit with radiation levels high enough to destroy DNA and quickly evaporate any atmosphere. The behemoth star is not a fan-friendly star. It's like a fire that spews out heat, light, and death into space. This kind of giant star has convective instability, which means that it goes through waves of light and dimming. Each change could be a sign of a change in the star's interior, a sign that it is about to fall, explode, or have some other end we don't know about yet. So why do we study something that scares us so much? Because the behemoth star can help us figure out how the universe's biggest stars live and die. We can see something that only happens in a few places in the universe, thanks to how bright it is. It's a slow-motion look at the end of the stars, and it helps scientists figure out how galaxies change over time. The dust envelope, a 1 light-year-long cloak of death. This kind of dust doesn't just appear out of nowhere. It comes from violent chaos. As the last steps of nuclear fusion happen in the behemoth star, it sends a huge amount of material into space. This includes gas, plasma, and heavier elements that were formed in the star's very hot core. These ejections cool down very quickly and turn into tiny dust grains made of silicates, carbon compounds, and other elements that don't easily melt. Astronomers call this a circumstellar dust jacket. The grains build up over time into a shell. But the behemoth star's envelope is no ordinary halo. In 2007, observations from the Very Large Telescope revealed something unexpected. The dust isn't evenly distributed. Instead, it takes the form of a toroidal, donut-shaped structure, suggesting that powerful stellar winds or magnetic fields are funneling material into specific directions. It's almost as if the star is wearing a cloak, one tailored by rotational physics and stellar instability. This torus doesn't just block the view, it also changes the type of light the star gives off. A lot of the behemoth star's energy is absorbed by the dust and then sent back out in the infrared. This is why the Spitzer Space Telescope and infrared spectroscopes on Earth are so important for figuring out what it is. Without them, the behemoth star would be mostly unnoticeable, like a beast that is hiding in plain sight. Then there's the weight of it. Astronomers think that the dust cloud holds between 3 and 9 solar masses of material that has been thrown out. That means the behemoth star has already lost more matter than most stars ever have, which is a stunning sign that it is nearing the end of its life. As if a god were dying, it leaks energy and matter into nothingness every second. What does a light-year-wide dust shell mean for the space around it? Catastrophe. The radiation from the behemoth star pushes this dust outward, driving a deadly shock front that sterilizes the region. If a planet ever existed nearby, it would now be buried under layers of radiation-scarred debris and vaporized molecules. There is no safe distance from a star like this, only different degrees of destruction. That's not all. This dust bag isn't just a grave monument. A cosmic event is about to happen. There will be no way to describe how strong the shockwave will be when the behemoth star finally goes supernova. The clash that happens will light up the dust like a torch, making a nebula that could be seen across worlds. It will be a cosmic echo and the last burning memorial to a star that was never meant to have a life. The Hayashi limit. Why the behemoth star shouldn't even exist. The Hayashi limit would be in bold if the world had a set of rules. In the study of stars, there is a limit to how big a star can get before it loses hydrostatic equilibrium. This is the careful balance between the pull of gravity and the push of heat pressure. This limit should be like a wall for red supergiants like the behemoth star. The behemoth star doesn't just lean against it, though, it gets rid of it. Named after Japanese astrophysicist Chushiro Hayashi, the Hayashi limit is a line on the Hertzsprung-Russell diagram, beyond which stars become unstable. According to the limit, low-mass, cool stars like red dwarfs and red giants can't expand past a certain radius without collapsing or shedding mass to regain balance. For high-mass red supergiants like the behemoth star, this means there's a maximum size they should be able to maintain without falling apart. But the behemoth star? It doesn't follow this general rule. Since its diameter is about 1,540 times that of the Sun, it doesn't just touch the Hayashi limit, it stomps all over it. There's no way it can stay together, though. Not really. How then does a star break one of the most basic rules of stellar physics? The dust layer and mass loss are the keys. Because the behemoth star is so fragile and swollen, it keeps losing mass at one of the fastest rates ever seen. Its upper layers stay cool because of this heavy mass loss, which keeps it from falling under its own gravity. For now. It's basically burning the candle at both ends, using outflows and dust distribution to keep a building stable when it should have already fallen apart. Astronomers also speculate that the star's rotation, magnetic fields, or even a potential binary companion, yet unconfirmed, could be influencing its bizarre behavior. These extra factors might be redistributing angular momentum or altering internal convection, giving the behemoth star a temporary extension on its stellar lifespan. It's like watching a massive building sway violently in the wind and somehow not fall. In a way, the behemoth star exists in open rebellion against theoretical physics. It's a cosmic outlaw, a star so massive, so luminous, and so unstable that it mocks the constraints of the models designed to describe it. And that's exactly what makes it scientifically invaluable. When you find an object that breaks the rules, you don't dismiss it. You study it harder. Because understanding why it doesn't fit might lead you to rewrite the rules altogether. The star that's falling apart. Extreme mass loss. The behemoth star isn't just big, it's also leaking. In a dramatic, slow and steady way, this huge star is pulling itself apart, throwing off its outer layers into space. This is what astronomers call mass loss, and the behemoth star has one of the worst cases ever seen. The star is breaking down into its own dust, like a mythical giant falling apart from the weight of being so big. Every star sheds some mass over time. Our Sun loses around 4.3 million tons of material every second through its solar wind. That might sound massive until you consider the behemoth star, which is losing matter at a rate thousands of times higher. Observations suggest it could be ejecting material at a rate of up to 10⁴ solar masses per year, meaning it expels the equivalent of Earth's mass every few weeks. But where is all that material going? The answer lies in the massive opaque dust envelope that now shrouds the star. This dusty cocoon, measuring up to a light-year in diameter, is made from the expelled gases and elements, cooled and clumped into complex molecular structures. It obscures much of the star's visible light, rendering it ghostly and dim from Earth, despite its monstrous size and luminosity. Not only is this mass loss amazing, it's also deadly. The way a star is put together is a very fine balance. When mass moves away from the star's outer layers, it changes the pressure differences inside the star that keep it from falling in on itself. This means that the behemoth star's time is almost up. The star is dying faster because of its strong, slowly moving winds and random outbursts of matter. The main reason for this instability is that the behemoth star has a swollen atmosphere and low surface gravity. The star has a very large radius and a very low mass, which makes it hard for gravity to hold on to its upper layers. When you add in strong stellar pulsations, radiation pressure, and maybe magnetic field interactions, you get a shell around a star that is always boiling over and letting mass escape into space. These mass loss episodes likely come in waves, with periods of relative quiet followed by violent outbursts. Think of it like a dying volcano, quiet one moment, erupting the next. And each time it erupts, it loses more of itself to the cosmos. As the outer layers thin, the core of the behemoth star becomes more exposed, inching ever closer to a catastrophic gravitational collapse. It's also beautiful in a strange way. The materials that were thrown out add carbon, oxygen, nitrogen, and stronger elements to the area around them, which are essential for life. Galaxies live because stars like the behemoth star die. With their last breaths, they leave behind the building blocks of planets, seas, and even living things that can feel pain. But for the behemoth star, it's a slow death that is both beautiful and sad. Every pulse of mass that is thrown out is a tick on the clock, and every dust wave is a whisper that the end is almost here. And when it does happen, the end could be one of the most terrible things everyone has ever seen. Star spectra and dust, secrets in the light. Astronomers figure out what this huge star is hiding by using a language called stellar spectroscopy. They do this by using cameras that are tuned to analyze sunlight to peel back its layers, rather than their hands. They found a very complicated mix of radiation, gas, and dust that is very different from anything else seen in the universe. At first glance, the spectrum of the behemoth star appears chaotic. Its light is reddened and dimmed, much of it absorbed and scattered by the dense dust envelope surrounding the star. This makes direct observations in the visible spectrum nearly impossible. But when astronomers turn to infrared and radio wavelengths, the curtain lifts. When huge telescopes like those at the European Southern Observatory split the behemoth star's light with prisms and filters, the chemical fingerprints of its atmosphere can be seen. Each of these spectral lines corresponds to a different element or molecule, making them like cosmic IDs. scientists have found silicon monoxide, SiO, carbon monoxide, CO, and water vapor through them. They have also found signs of more complicated molecules forming in the dust shell. What's astonishing is not just the presence of these molecules, but the conditions under which they exist. The surrounding dust cloud isn't just passively floating, it's actively radiating energy, heated by the intense luminosity of the behemoth star. Some of this radiation gets re-emitted in infrared wavelengths, creating an eerie glow that helps map the structure of the envelope. Researchers believe this dust shell forms a toroidal, donut-shaped structure, possibly sculpted by rotating mass-loss jets or an unseen companion star. Temperatures inside this bright ring can be anywhere from a few hundred to over 1,000 degrees Kelvin. These temperatures are cool compared to the star itself, but they are hot enough for dust grains to form and change. In these places, the building blocks of planets and solar systems of the future are formed, long before they ever come together to form rock or flame. Spectroscopy also reveals the velocity of materials moving around the star. Some spectral lines are redshifted, indicating gas flowing away from us. Others are blue-shifted, revealing matter being ejected in our direction. These asymmetries suggest that the mass loss isn't uniform. The star could be shedding material in bursts, along different axes, or influenced by magnetic fields or rotation. It's interesting that the behemoth star's spectrum has emission lines that shouldn't be there, at least not in this type of star. Based on these lines, it looks like shock waves and high-energy reactions are happening in the area around it. It's like the star is constantly shaking inside, with each wave shaking things up and setting off strange, short-lived chemical reactions. Even with all of this going on, the behemoth star is still not very bright. So much dust surrounds the star that it hides the photosphere, which is the real surface that we can see. We don't see the star itself. What we see is a soft glow through a cloud of smoke. This is light that has been colored and filtered by gas and dust. The hunt for companions. Is the behemoth star a binary star? We already know that the behemoth star is one of the most extreme stars we've ever found. But what if it's not the only one? Astronomers have been quietly wondering for years if this red supergiant has a partner star that is hidden somewhere in its thick cloud of dust. If it's true, it would completely change everything we know about this monster from the sky, from how it is now to what will happen to it in the end. The idea has been used before. Most of the time, massive stars form in groups of 2 or 3. Not only are binary star systems widespread, they are thought to be the standard for how high-mass stars form. These very large items are held together by gravity, sometimes dancing very close to each other and sometimes very far apart. One thing that makes the behemoth star so strange is that its dust envelope is hard to see. This makes the search more difficult. This dust covers space like a blanket, blocking and spreading visible light. This makes it very hard to observe with regular telescopes. Scientists do have some very useful tools, though. There may be hints in infrared imaging, radio interferometry, and spectroscopic velocity changes. One of the most important signs of a binary system would be finding irregular wobbling, which are small changes in the behemoth star's motion caused by the pull of a partner. But so far, the evidence has been inconclusive. Some studies have reported asymmetries in the dust shell, strange lopsided structures that could be shaped by the presence of a nearby stellar object. The toroidal dust formation around the behemoth star is particularly intriguing. It resembles the kind of material outflow we often see in binary systems, where one star's winds are sculpted by another's gravitational influence. More recently, observations with the Very Large Telescope Interferometer, VLTI, hinted at disturbances in the dust envelope that could be caused by a nearby object. Some models even suggest that if a companion star exists, it might be a hot O-type main sequence star, small compared to the behemoth star, but still massive and powerful in its own right. This hypothetical partner could be orbiting inside the dust cloud, feeding off the red supergiant's expelled material like a parasitic twin. If that's the case, The behemoth star would be a binary mass transfer system, where gas and dust from the larger star flow toward the companion, potentially fueling accretion disks or even triggering X-ray emissions. But detecting those X-rays is tricky. The behemoth star's dust shell is so thick that it likely absorbs most of them before they ever escape. Another clue might come from polarization data, light from the star that's been scattered by dust and gas in a particular way. Some of these observations suggest a non-spherical distribution, again raising the possibility of external forces shaping the flow of matter. No straight images of a partner star have been made. It has not been proven that there are any regular radial velocity trends. It looks like the question isn't whether the behemoth star could have a friend, but whether we can find it through the veil. It changes the whole ending if the behemoth star is part of a binary system. A partner could speed up the loss of mass, change the way it goes supernova, or even help make a lopsided explosion happen. Galactic supernovae are some of the strongest explosions ever seen in the universe. They happen when two very large stars in close orbit join. When stars defy physics, stellar structure, and collapse. The behemoth star is a star who doesn't follow the rules. Literally and figuratively, it's on the edge of what we know. It's trying the limits of what a star can be without falling apart. In many ways, it's a cosmic paradox. The star should have already fallen or burst by now, but it still exists in a state of unstable balance. Before we can figure out how the behemoth star goes against the laws of physics, we need to look at what stellar structure really means and what happens when it starts to break down. No matter how big a star is, it has to balance between two huge forces, gravity and pressure. The star is always being pulled in by gravity, which is trying to turn it into a tight ball. On the other side is the pressure from nuclear fusion, which shoots outward as hydrogen atoms in the core fuse into helium, releasing energy. For most of a star's life, these forces don't change. Not for the behemoth star, though. This red supergiant has pushed its structure to a breaking point. Its enormous size, over 1,500 times the radius of the Sun, means its outer layers are incredibly diffuse, hanging on by the thinnest gravitational thread. Its surface is so extended and low density that it's no longer a tidy spherical ball of gas. Instead, it's more like a pulsing, wobbling cloud, with parts of its atmosphere literally leaking into space. Complicating things further is the Hayashi limit, a theoretical boundary that marks the maximum radius a star of a given mass can have, while still remaining in hydrostatic equilibrium. The behemoth star may lie beyond this limit, a place where no star should stably exist. This suggests that its internal structure is unstable, perhaps already undergoing convection-driven mass ejection or core instabilities that will inevitably end in collapse. Inside the star, fusion has long since moved past hydrogen. Helium is being fused into carbon and oxygen, and deeper still, heavier elements like neon, magnesium, and silicon begin to form in quick succession. Each new stage of fusion is shorter than the last. A star like this can go from silicon fusion to collapse in just a matter of days. And yet, it's the very mass of the behemoth star that prevents it from stabilizing. The sheer gravitational pressure at its core is overwhelming, and it's pushing the star into a zone where fusion becomes erratic. The core becomes degenerate, meaning pressure no longer depends on temperature, but on the quantum state of the particles within it. At this point, the laws of normal thermodynamics start to break down. The core can't hold itself up against gravity once it hits the Chandrasekhar limit, which is about 1.4 times the mass of the Sun. If the behemoth star keeps going in this direction, it will experience core collapse, a dramatic and violent event in which the inner layers contract and then return, setting off an unimaginable supernova explosion. It's not easy to fall apart, though. Pulsations, short-term contractions, and swells of the behemoth star may happen because of uneven pressure and gravity. These pulsations could cause huge releases that shed solar masses of matter all at once. Stars might not turn into black holes if they lose enough mass before they fall apart. Instead, they might turn into neutron stars. If not, it turns into something much scarier. The end of all things, from red giant to supernova. There are deaths in every star, but some deaths are heard all the way across the universe. That ending won't be quiet for the behemoth star. It will be like a nuclear explosion in the universe, releasing so much energy that it will shine brighter than whole galaxies and turn night into day for any neighboring society for a short time. We have to go into the heart of a dying star to understand how the behemoth star ends. The core of the behemoth star turns into a nuclear pressure cooker as the fusion engine burns through its fuel. Helium fusion has given way to carbon, neon, oxygen, and finally silicon fusion, which is the last step before collapse. Hydrogen has been used up for a long time. Silicon fusion doesn't last very long, though. It might only last a few days in a star this big. Iron is the most stable element. It doesn't release energy when fused. This means that once a core is dominated by iron, fusion can no longer support the star against gravity. The engine stops. Gravity wins. The core collapses inward at a quarter of the speed of light, crushing matter into a state of unimaginable density. In just seconds, the core becomes a neutron-rich ball, smaller than a city but heavier than our sun. Then comes the rebound. The collapsing core slams into itself and bounces back outward, sending a shockwave through the star's outer layers. This shockwave, combined with a flood of neutrinos pouring from the core, tears the star apart in a supernova explosion. The brightness of such an event would be staggering. For a few weeks, the behemoth star's death would be visible across galaxies. On Earth, it might outshine the moon, casting shadows at night, visible even during the day, like a false sun. Astronomers would scramble to study the supernova's light curve, its chemical signatures, and the incredible speed of its expanding debris. What's left behind depends on how heavy the star is after it sheds its outer layers. Stellar winds and releases could have caused the behemoth star to lose enough mass that the core could now be stable as a neutron star, which is so dense that a teaspoon of it would weigh billions of tons. Neutron degeneracy pressure will not work if there is still too much mass, though. Then it turns into a black hole, which is a scar in space-time that you can't see that eats light, time, and matter. The supernova residue will spread out into space, adding heavy elements like gold, uranium, and platinum to the medium between the stars. Everything you have, from your bones to the thing you're holding, was made when stars like this one died. These enormous deaths aren't just the end. They're also the start of something new, giving galaxies the building blocks for life. Could the behemoth star become a black hole? When massive stars die, their cores collapse. If the remaining core is less than about 2.5 times the mass of our Sun, it becomes a neutron star, held up by the quantum pressure of tightly packed neutrons. But beyond that threshold, if the mass is too great, the collapse doesn't stop. Gravity overcomes even neutron degeneracy pressure. The star shrinks not just to a city-sized object, but to a mathematical point, a singularity. This is how a black hole is born. Where does the behemoth star stand then? Its mass is thought to be between 25 and 40 times that of the Sun right now. Some red supergiants, like the behemoth star, lose a lot of matter as they get close to the end of their lives. This happens through strong star winds and mass loss events. Some of this stuff is thrown out in huge clouds of dust and gas, the same clouds that are now covering the behemoth star in a thick, cloudy haze. This covering makes it hard to get a clear picture of its exact weight. But its core is almost certainly still too heavy to be a neutron star, even if it has lost half of its original mass. In other words, the behemoth star is a prime black hole candidate. But this isn't just a theoretical prediction, it's a cosmic inevitability. Black holes are not rare exceptions. They are the logical consequence of massive stellar death. And for a red hypergiant as extreme as the behemoth star, collapsing into a black hole is the most probable outcome. When it happens, it will be silent. After the initial supernova flash fades, the core's gravity will win completely. In the final moments, Space-time will fold inward. Matter will disappear. Information, according to some physicists, may be lost forever, though quantum theories like Hawking radiation suggest that's not the whole story. The new black hole could be anywhere from 5 to 15 solar masses in mass, but its radius would be just tens of kilometers across. That's smaller than most cities, yet with gravity so strong it could bend light, slow time, and distort reality itself. In the event that it has a partner star, it will become opaque. Then the black hole might pull matter from the nearby star, making a bright accretion disk and sending out strong X-rays. It could even send relativistic jets into outer space, which would shoot matter into space at almost the speed of light. It's more likely that the behemoth star's black hole will just drift along in silence, soaking up gas and dust as it goes. It will grow slowly over eons. It could someday join other black holes at the center of a galaxy or crash into another black hole, sending gravitational waves through the universe. Ui Scuti, another monster, but still not the largest. Before the name Stephenson 2-18 began appearing in astronomy textbooks, before the behemoth star loomed large as the shadowy titan in the Large Magellanic Cloud, there was Ui Scuti, the reigning record holder for the largest known star by radius for several years. If the behemoth star is the mysterious colossus hidden behind veils of cosmic dust, then Ui Scuti is the flamboyant emperor, seated regally in the heart of the Milky Way, glowing like a ruby in the galactic crown. Located approximately 9,500 light-years away in the constellation Scutum, Ui Scuti is a pulsating red supergiant, and its size borders on the unfathomable. Estimates of its radius have placed it at around 1,700 times larger than the Sun. This would mean that if Ui Scuti were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, devouring Mercury, Venus, Earth, Mars, and possibly even Jupiter itself. Ui Scuti is more than just big, it's also incredibly luminous, radiating about 340,000 times more light than the Sun. And yet, despite its size and brightness, it is not the most massive star in the universe, not even close. In fact, its mass is relatively modest for a star of its class, clocking in at only around 7 to 10 solar masses. How is that possible? The answer lies in how dense the stars are. Like many other red supergiants, Ui Scuti has a very low density. It's like a cosmic bubble. If you stood on the surface of Ui Scuti, if there is such a thing, you'd be floating in a soup of plasma because its upper layers are so thin and spread out. In some ways, it's more like an environment than a star. Instability and fast mass loss are also signs of a red supergiant. It is thought that Ui Scuti will end its life in a huge supernova, but no one is sure when that will happen. Some guesses say it could happen in the next million years, which is pretty much today in cosmic terms. The star also serves as a cautionary tale for the difficulty of stellar measurements. Since its discovery and classification in the 20th century, subsequent observations have caused astronomers to revise its estimated size, sometimes making it appear smaller than other contenders. These fluctuations are due to factors like pulsations, dust interference, and measurement methods, particularly in determining the outer edges of its vast, tenuous atmosphere. So is Ui Scuti still the largest star we know? That depends on your metric. In terms of radius, it's a record breaker, at least within our own galaxy. But it's now being challenged and perhaps surpassed by stars like the Behemoth star and Stephenson 2-18, which may be even larger and more extreme. Ui Scuti has earned its place in the Celestial Hall of Fame. It reminds us that size and mass are not always the same thing, and that the universe can build giants from gases so diffuse their bodies barely cling to themselves. Vi Canis Majoris, the ghost of a former record holder. For a long time, Vi Canis Majoris was the biggest star known. It was a red supergiant. It was the biggest star before Ui Scuti, Stephenson 2-18, or the Behemoth star came along. It is now a myth covered in twilight, a dying titan in the constellation Canis Major, that is moving toward the end of its cosmic story. VI Canis Majoris is a star system about 3,900 light-years away that is often described as mythical in size. It is thought to have a radius over 1,400 times that of the Sun when it is fully expanded. This means that if it were dropped into the center of our solar system, it would reach far beyond Jupiter's orbit. It's so big that more than 2 billion suns could fit inside it. But like many red supergiants, its low density means it's not as massive as one might assume. Its mass has been estimated at around 17 times the mass of the Sun, which is not extraordinary in terms of stellar heft. What makes it terrifying is how unstable and violent it has become. VI Canis Majoris is what astronomers call a high mass loss star. It's shedding its outer layers at a furious pace, losing material into space through immense solar winds that have created a vast nebula of expelled gas and dust around it. This envelope is not a soft breeze. It's a hurricane in space, ejecting matter with more force than any natural process on Earth. The result is a star that looks like it's disintegrating from the outside in. There are signs of this amazing process. The light from VI Canis Majoris flickers and dims, not because of changes inside it, but because the clouds of dust circling it are moving around. Trying to see the star is like trying to see through a storm. The clouds change its brightness and perceived size, making it hard to get accurate measurements. This is one reason it stopped being the biggest star. Newer readings point to a smaller radius than was once thought, but no one is sure. In spite of this, VI Canis Majoris is still a key part of how we understand star death. Most likely, it is about to explode into a supernova or even a hypernova, just like the Behemoth star and other huge stars. When it does, the explosion will likely be brighter than the full moon for weeks or even months, making it visible from Earth. The show will light up the sky and give us important information about how red supergiants die. It's not just its size that makes it special. VI Canis Majoris has also made us think about how stars die in new ways. It's too heavy to live for long and too unstable to stay alive, but it's still holding on in one of the most extreme star states scientists have ever seen. If the Behemoth star is the beast in the cosmic fog, and UY Scuti the fading king, then VI Canis Majoris is the ghost of glory past, a once undisputed monarch, now veiled in decay, and destined for one final act of luminous violence. And when it goes, it will not die quietly. It will go out in a blaze that reshapes everything around it, a true death worthy of the star it once was. Stephenson 2, 18, the only star that might be bigger. Discovered in the 1970s and located roughly 19,000 light-years away in the constellation Scutum, Stephenson 2, 18 is a member of a massive stellar cluster known as Stephenson 2. It's one of the most luminous red supergiants we've ever observed, radiating with a light output that is at least 440,000 times brighter than the Sun, although some estimates push that number even higher depending on the assumptions about dust and distance. That being said, its mass might not be as big as its bulk makes it seem. Like other red supergiants, Stephenson 2, 18 is swollen, and gravity only holds its upper layers in place very loosely. Most likely, it has a mass of 40 to 50 solar masses, which is pretty big but not as big as some other small stars. This difference between mass and size shows how misleading volume can be in the universe. The star is like a huge balloon, vast and puffy, but not as heavy as its scary looks would lead you to believe. The fact that we don't know much about Stephenson 2, 18, is what makes it so interesting. Because it is so big and far away, most of our readings are based on indirect methods, such as brightness, temperature, and theoretical models that tell us how far away it is. The Milky Way's dust and gas cover some of the cluster it lives in, making things even less clear. Even with these problems, it is still a contender. It might be the biggest star that humans have ever measured. And it's not just big. It's also ancient, at least by the standards of massive stars. Stephenson 2, 18 is nearing the end of its life, and when it dies, it won't go quietly. It could explode as a supernova or even a hypernova, potentially leaving behind a black hole in its wake. Given its massive envelope and proximity to the theoretical limits of stellar structure, it's a prime candidate for producing one of the most energetic stellar deaths in the universe. So is Stephenson 2, 18 truly the largest? The answer is maybe. Stellar giants are notoriously difficult to measure with absolute certainty, and changing models can shift the rankings. But whether it's the absolute biggest or not, Stephenson 2, 18 is a monumental milestone in the story of cosmic scale, a flaming colossus that embodies the extremes of stellar evolution. Mu Cephei, the red king of our galaxy. Mu Cephei, which is sometimes called the garnet star, is one of the brightest stars in our sky. Its beautiful color makes it stand out. This red supergiant is in the constellation Cepheus and is one of the darkest red stars that can be seen with the human eye. Astronomer William Herschel once called it deep garnet because of how bright it is. But Mu Cephei is also a huge force. Its diameter is thought to be about 1,260 times that of the Sun, which makes it one of the biggest known stars in the Milky Way. A planet called Mu Cephei would have a photosphere that is about the same size as the paths that Jupiter and Saturn take around the Sun. Its size would be big enough to hold billions of Earths, and even though it's not the biggest star ever found, it's still a giant. Mu Cephei is around 6,000 light-years away, and its distance has long been a subject of debate, which makes calculating its exact size difficult. Nevertheless, its enormous luminosity, roughly 350,000 times that of the Sun, and relatively cool temperature of around 3,500 Kelvin, suggest it is nearing the final stages of its life. Red supergiants like Mu Cephei are old stars, having exhausted most of their hydrogen fuel and now fusing heavier elements in their core. The fact that Mu Cephei has lost so much mass over time is very interesting. It is losing its upper layers into space at an incredibly fast rate, just like the behemoth star and other red giants. This creates a stellar wind that moves matter through the space between the stars. This process not only changes what will happen to the star in the future, but it also helps recycle elements in space. Carbon, oxygen, and heavy metals that are thrown out will eventually form new stars and planets, keeping the cycle of life going. It is likely that Mu Cephei will go supernova when it dies, leaving behind either a neutron star or a black hole. As of right now, it's still a bright guardian in our galaxy, a warning that monsters live even close to where we are. The blue supergiants burn bright, die fast. While red supergiants like the behemoth star and Mu Cephei loom vast and cool, there's another class of stellar monsters that trade lifespan for intensity: blue supergiants. These are some of the hottest, brightest, and most short-lived stars in the universe, burning with such ferocity that they often don't survive long enough to grow large in size. But in terms of raw power, they are unmatched. Imagine a star so luminous it can outshine an entire galaxy from the right angle. Rigel is one of the most well-known examples. It is the biggest star in Orion and one of the sky's brightest stars overall. Rigel is about 120,000 times brighter than the Sun and has a surface temperature of about 12,000 Kelvin. It is a bright blue-white star in the sky. Rigel is very big, but it's only going to live for a few million years, a very short time in the grand scheme of things. Because these stars use up their nuclear fuel so quickly, they often explode as supernovae before they can get as big and cold as red supergiants. What makes blue supergiants so powerful is their massive cores. These stars often start their lives with masses 20 to 50 times greater than the Sun, sometimes even more. This enormous mass leads to a gravitational pressure so great that fusion reactions occur at incredible rates, turning hydrogen into helium and eventually into heavier elements at breakneck speed. The intense radiation pressure from these reactions tries to blow the star apart, but gravity fights back in a precarious balance. When the fuel begins to run out, that balance tips violently. Red giants grow and cool down before they die. But blue supergiants often explode in a very bad way. Some of them break into Type II supernovae, and the biggest ones might send out long gamma-ray bursts, which are very powerful beams that could wipe out all life on Earth if they hit it. Luckily, there aren't any blue supergiants close enough to Earth right now that could cause that kind of show. But even so, their deaths are very important. The stuff that comes out of a blue supergiant supernova is full of heavy elements, like the iron, calcium, and gold that are in our bodies and on Earth. Even though their lives are short, these burning giants are like alchemists in the universe. They turn the lightest elements into the stuff that planets and people are made of. Astronomers are still looking into these stars to learn more about how mass, temperature, and brightness affect each other in very harsh stellar settings. We still don't know a lot, especially about the last few seconds before the building fell. It's possible that some blue supergiants will not even go through the visible supernova phase. Instead, they will collapse straight into black holes and disappear in an instant, leaving no sign. Blue supergiants are some of the most interesting things in the sky because they are so rare, so bright, and so dangerous. The yellow hypergiants, rare and furious. The yellow hypergiants are some of the most unstable and poorly understood stars in the universe. They are like mythical beasts that don't just fit into any category, they change it. If red supergiants are like huge titans and blue supergiants are like burning infernos, then yellow hypergiants are like the gods of cosmic storms. They are always changing, losing mass, and standing on the edge of destroying themselves. They are very rare. Only a few are known to exist in our galaxy. Their lack of numbers is more than made up for by their mystery and the fact that they could go off at any time. Yellow hypergiants are an unstable stage in the development of stars that are usually between the red supergiant and blue supergiant stages. The bright color of these stars doesn't last long. Their surface temperatures are between 4,000 and 8,000 Kelvin, which puts them in the F and G spectral classes. This is similar to how our Sun is classified, but their brightness is hundreds of thousands of times stronger. They are so bright that the top layers are barely holding on. Huge solar winds and dramatic mass ejections are constantly ripping them apart. Take Rho Cassiopeiae, for instance, one of the best-studied yellow hypergiants in the Milky Way. It's around 500,000 times more luminous than the Sun and sits roughly 4,000 light-years from Earth. This star has been observed undergoing massive outbursts, during which it ejects several Earth masses of material in just a few months. These violent episodes dim the star significantly as its brightness gets choked by the thick clouds of expelled gas and dust. It's like watching a star try to tear itself apart in slow motion. Another notable yellow hypergiant is HR 5171, a bloated monster so large it would stretch beyond the orbit of Jupiter if placed at the center of our solar system. It's part of a binary system, and astronomers have detected mass transfer between the two stars, possibly spiraling them toward a future collision or merger, an event that could result in a supernova or even something more exotic, like a Thorne-Zitkow object, a hybrid star formed from a neutron star swallowed by a supergiant. Why don't we see many yellow hypergiants? Because this phase is very short, a blink on the cosmic clock. It lasts only a few tens of thousands of years. Stars that are big enough to reach this stage already live quickly and die young. At this point, they're going through a cosmic identity crisis, going back and forth between being unstable and collapsing. But by looking at these unstable giants, scientists learn new things about how stars lose mass, how circumstellar envelopes form, and how supernova blasts start out chaotic. Yellow hypergiants often send thick rings of gas into space. These nebulae are full of heavy elements and dust and help make the universe a better place for new stars and planets to form. Could planets orbit a star like the Behemoth star? The planets that circle the Behemoth star would have to be very far away from it. The star is so big that its surface would go beyond Jupiter's orbit if it were put in the middle of our solar system. Any planet that used to be in the inner solar system, like Mercury, Venus, Earth, or even Mars, would be destroyed or eaten by the expanding stellar atmosphere. Even very far away, the heat and radiation that the behemoth star gives off would be too much for life as we know it to survive. But could there be planets farther away, in the area of gravity outside the giant's bright surface? It's possible, yes. There is no rule that says planets can't form around a red supergiant. But the star's unstable mass loss, stellar winds, and dust bands make it unlikely that a planetary system could stay stable. This is especially true for systems with moons or orbits that are very delicate, like ours. The behemoth star is known to be losing mass at an extraordinary rate, casting off solar material at speeds and volumes that dwarf even the most active stars in our galaxy. These violent stellar winds would exert drag on any nearby orbiting bodies, potentially sending them into decaying orbits or out into interstellar space. Even if planets once formed around the star in its earlier, more stable years, they may have already been swept away by its current phase of expansion. Also, the gravity field around the behemoth star is very different from that of a main sequence star. The star's low surface gravity and huge radius make its gravitational grip on close objects not very strong compared to its overall mass. This makes a thin, unstable zone, a kind of chaotic circling shell, where dust, debris, or rogue planets could stay for a short time before being sucked in or thrown away. Still, if planets did make it to a safe distance, say far beyond the distance of Neptune's orbit in our solar system, they would see something very strange in the sky. The star would be the brightest thing in the sky, covering a huge part of the viewable dome and giving off a deep red light. It would be covered in clouds of moving, constantly changing stellar dust. There would be no real nights, just times of slightly less intense red dusk. And while such a world might be geologically frozen due to its distance, it could still be bathed in intense radiation from ultraviolet and X-ray flares if the star became unstable. If life did exist there, it would have to be radically different from anything we know, perhaps shielded deep underground, or evolving under biochemistries we've never imagined. What would life be like on a world near a supergiant? Visualize being on a world that circles a red supergiant like the behemoth star. It wouldn't be blue in the sky above you. It would be red. There wouldn't be any stars or constellations to see. There was only a huge ocean of red-orange light coming from a star that took up half the sky. Day and night? Don't bother. There is no night here. There are only different levels of redness, and that's just the start. Living near a supergiant is very different from life on Earth. It goes against almost all of the rules we think of when we think of a world with life. Just the light would be enough to change the beat of time. The daily routine of light and dark controls everything on Earth, from how plants grow to how people sleep. In a world that orbits the behemoth star, there might not be a diurnal cycle, photosynthesis, or a real difference between day and night. Now, let's talk about temperature. Even at a significant distance, the radiation from a supergiant would raise surface temperatures on nearby worlds to unlivable levels. Any atmosphere would need to be extremely thick or shielded, rich in reflective aerosols or high-altitude clouds, just to avoid being stripped away by the intense stellar wind. The radiation pressure from the behemoth star is so high that even dust and gas around the star are constantly being pushed outward, so any unprotected biosphere would be in constant danger of erosion or sterilization. Let's say that life did start to appear in that kind of world. We wouldn't do that. Forget people who live on the top. Life underground would be much more likely. Deep layers of rock, thick seas, or thermal vents where heat is more stable and away from the chaos of the stars above could all be places where life could start. It's possible that these living things don't need sunshine, and instead use chemosynthesis to get energy from minerals or volcano heat. Alternatively, organisms might adapt by incorporating radiation-absorbing pigments into their biology, essentially living solar panels capable of turning extreme radiation into usable energy. Some extremophile bacteria on Earth already do this in small ways. Imagine scaling that up for a species that thrives beneath a red sun that never sets. Then there's the issue of planetary orbit. The massive gravitational pull of a red supergiant is complex and unstable. Planets would likely be in elongated orbits, creating massive seasonal variations. One side of the year could be blisteringly hot, the other a frozen wasteland. Life would have to be incredibly resilient, hibernating, adapting, or rapidly evolving with each cycle. After that, there's the clock above you. It doesn't last forever for a star like the behemoth star. Our sun's lifespan is measured in billions of years, but its is only measured in millions. It's like a time bomb. It will eventually go supernova, sending out a wave of energy that will destroy everything within dozens of light years. Any planet that happened to be close would be destroyed, and its atoms would be thrown into space, where they would help make new stars and planets. Could there be life close to a supergiant? In theory, yes, but only if it's deep, protected from radiation, and doesn't last long. It would live under a sky of doom, though, and always know, if it could know, that its life was short, like a spark burning in the shadow of something too big to be real. Radiation hellscape. Why these stars are deadly to life. If a red supergiant like the behemoth star seems awe-inspiring from afar, it becomes terrifying up close, not because of its size alone, but because of the unrelenting storm of radiation it unleashes. These massive stars are not peaceful giants. They are furnaces of chaos, broadcasting waves of deadly energy across the cosmos. Any attempt at survival near them would be like trying to build a home next to an open nuclear reactor without the protective shielding. Let's start with ultraviolet radiation. Massive stars emit enormous quantities of it. While our sun emits UV light as well, the Earth's atmosphere filters most of it out. Near the behemoth star, the sheer intensity of UV radiation would strip away planetary atmospheres, rendering them sterile and lifeless in short order. There's no ozone layer that could possibly keep up. If Earth orbited such a star at a similar distance as it does the Sun, life would be reduced to carbon ash in seconds. Then there's X-ray and gamma-ray radiation, the truly lethal kind. As the behemoth star nears the end of its life, its unstable core will churn out higher energy emissions. These rays don't just kill cells. They destroy DNA on contact, making complex life almost impossible. Exposure to these would result in radiation poisoning, sterilization of entire ecosystems, and complete atmospheric ionization. There's no protection without a planetary-scale magnetic field orders of magnitude stronger than Earth's, and even then, it might not be enough. But the danger doesn't just come from the direct emissions. Stellar winds, which are made up of charged particles thrown out at very high speeds, would hit any planets close and damage them. Over time, these winds could wear away at a planet's atmosphere, which is what keeps space weather out. Cosmic rays, sun particles, and plasma storms can all take away a planet's atmosphere molecule by molecule once that layer is gone. Because the behemoth star has such a huge dust envelope, it hides many of its own risks behind a cloud. A toroidal, donut-shaped cloud of dust and gas is formed when the star sends out so much matter. This might provide some protection, but it has two sides. That cloud spreads and returns radiation, making some areas more exposed to it instead of protecting them. It's like a hall of mirrors for death rays from stars. Supergiants aren't stable. They pulse, grow, shrink, and spew out huge flares. These bursts can temporarily increase the amount of radiation by hundreds or thousands of times. A single star tantrum could wipe out a world that may have become used to the background radiation. It's important to note that the behemoth star is in the Large Magellanic Cloud, which is a galaxy that is part of the Milky Way, but has a different makeup of chemicals than our own. In other words, the radiation output might not act the way we think it will, based on models from the area. This behavior by aliens adds unknowns to models of radiation, which makes these stars even harder to predict and more dangerous for everything close. In a universe where life clings to fragile stability, red supergiants like the behemoth star are the destroyers. They are cosmic final bosses, radiating death across the void not out of malice, but because of their sheer titanic nature. Life, as we understand it, does not survive in their shadow. Orbiting a monster. Gravitational tidal forces explained. If you lived in orbit around a star like the Behemoth star, you would be trapped by a cosmic beast that would twist, stretch, and crush anything that got too close. A supergiant like the Behemoth star has such strong gravitational pull that any close object would be sucked into a violent dance of distortion and decay. This is in contrast to our Sun, whose gravitational pull keeps the seasons and tides steady. Planets are held in place by gravity, but gravity also has effects on the inside of planets. The Behemoth star has such a strong gravitational field that it would pull a planet out of its orbit and even pull the planet itself if it was close enough. This is what tidal forces are, the difference in how much gravity pulls on different parts of a person. It can be seen with Earth and the Moon. The part of Earth that is closer to the Moon has a stronger gravitational pull, which makes the waves in the oceans. Now imagine that same effect magnified 1,000 times. Near the Behemoth star, a planet's solid crust could be stretched and compressed over and over, causing severe tectonic activity. Think super earthquakes, global volcanic eruptions, and possibly tidal heating so intense that the planet's core might stay in a perpetual molten state. We've seen this with Jupiter's moon Io, which is constantly reshaped by Jupiter's gravity, and that's a much smaller example. But the nightmare doesn't end there. If a planet orbits too close to this supergiant star, it risks falling into the Roche limit, the minimum distance at which a celestial body can orbit without being torn apart by tidal forces. Get too close, and the planet could be shredded into rings of debris, its matter pulled away in streams like ribbons around a maypole of destruction. A planet's orbit might not stay stable even if it stays outside the Roche limit. Not only is the Behemoth star very big, but it is also dropping mass very quickly because of radiation and star winds. Its gravitational pull on things in its orbit changes as it loses mass. This means that planetary orbits can move, spiral outward, or become eccentric, which means they are stretched out like ovals. These changing orbits cause big changes in the temperature, which makes it impossible to live there for a long time. Orbital resonance is another problem. This is when more than one moon or planet interacts gravitationally with the main star and with each other. In a system around a star as heavy and unstable as the Behemoth star, these resonances would be highly unstable and could throw planets out of the system or into the star. Don't forget about accretion rings either. A planet could get stuck in the accretion disk, which is a ring of superheated gas and dust that swirls around the Behemoth star as it nears the end of its life and starts to collapse into a supernova or black hole. That climate would kill the world with radiation and bring it closer and closer to being destroyed. All of this brings to light a scary truth. Circling the Behemoth star is not only dangerous, it's almost impossible to do without being destroyed, sterile, or thrown into space. If a planet gets too close, it gets caught in a trap of beautiful but strong gravity. And if life ever did appear in such a system, it would rest on a delicate balance that the universe doesn't care much about. Watching a star collapse from nearby hypothetical scenario. Think about this. You live on a faraway world, maybe near the edge of a solar system with the Behemoth star as its main star. You are far enough away that the red supergiant 280,000 times solar luminance won't burn you alive, but close enough that it looks like a bloated, blood-red globe in the sky with a surface that sparkles like boiling oil. It's been on for decades or even hundreds of years. However, things start to change. It starts out slowly, with a flash that sounds like a heartbeat stalling in the dark. The star dims a little and then gets brighter in a random way. Your first thought is that it's just one of its normal pulsations. After all, supergiants do that. But this time is different. The gaps get smaller. When the star's upper layers start to fall off more quickly, clouds of gas and dust start to blow off like cosmic steam. Readings from spectroscopy scream of catastrophic instability. It has started to fall apart. At this point, your skies go from beautiful to terrifying. Imagine looking up to see the behemoth star's outer atmosphere literally accelerating outward, expanding visibly even over the course of hours or days. The star begins to swell, not gracefully but chaotically. Flares explode across its surface, superstorms erupt, and magnetic fields twist into massive loops large enough to engulf entire planets. The night is no longer dark. The supergiant is brighter than any sun, even at your extreme distance. In a single moment of absolute violence, the core of the behemoth star collapses inward faster than light can escape the surrounding material. The collapse halts not with peace, but with a rebounding fury. The result? A supernova of such ferocity that it temporarily outshines the entire galaxy. You're not watching it on a telescope. You're watching it cast double shadows behind every object around you. Shockwaves are sent out into space, and if you're even slightly close, within a few dozen light years, say, the end of the world is about to happen. The strong burst of gamma rays goes through your environment and destroys all electronics, DNA, and any technology that might still be useful. If your planet has a magnetosphere, it will be very compressed, which will boil off your top atmosphere. Not if it doesn't. The surface has been cleaned, always, but say you're really, really far away, hundreds of light years away. You make it, not really. Your people have changed. You wait months to see what happens next. For months you see a bright cloud and the skeletal remains of a star that was once thought to be impossible. Gravitational waves are picked up by instruments. If the behemoth star fell into a black hole, those waves would have gone through your bones and changed the shape of space-time around you for a split second. The giant had been around for millions of years, longer than your society, and maybe even longer than life on your world itself. It's gone now, but from its death comes life. The heavy material that was thrown out starts to spread through space, making the building blocks for new stars, planets, and starts. It would not be a quiet or beautiful death to watch a star like the behemoth star fall apart from close by. It would be a dramatic, memorable, and awe-inspiring ending that would show that even the end of something huge can lead to new and amazing things. A light-year shadow, living in the behemoth star's umbra. Consider a star that is so huge and bright that it leaves a shadow a light-year long just by being there. With a dust package that covers almost 5.88 trillion miles, the behemoth star doesn't just shine, it rules. What would it be like to live in its umbra, the shadow it throws on the rest of the universe? Astronomers use the word umbra to describe the darkest part of a shadow, where no light can get through. On Earth, we think of it when we see eclipses, but in the case of the behemoth star, the umbra isn't a temporary event. It's a permanent area of darkness, whose thick, torus-shaped dust-covering blocks light from astronomically far away. Let's say your planet exists in a system just behind this dusty cloak, tucked into the cosmic veil. You wouldn't see the full, flaming face of the behemoth star. Instead, the sky might glow with a dull crimson twilight, not from direct starlight, but from scattered photons refracted and diffused through layers of interstellar dust. Day and night would blur together, with everything drenched in a reddish hue, like a planet forever suspended in the final moments of sunset. The temperature would be oddly mild. You're in the proximity of a stellar inferno, yet the dust and gas block much of the heat. Your world might orbit a secondary star, smaller and more manageable, because orbiting the behemoth star directly, even at great distances, would be like setting your planet next to a nuclear blast. But even your sky would not be free of the behemoth star's influence. Its radiation would leak in around the edges, its gravity gently tugging at your solar system, altering orbits over millennia. What's above would be the real show, though. At the horizon, or maybe even taking up half the sky, you'd see the bent shape of a giant covered in dust, filled with glowing gas and debris that pulsed slowly, like a god's last breath. Auroras may shine at your poles, but not from your star. Instead, they may be caused by the stellar wind and magnetic chaos coming off of the behemoth star. Meteor showers could happen often, with pieces of the dust disk falling like rain. It would be scary and holy in your myths. This isn't a star far away. This is a monster in the sky that lives and breathes. Its heart is hidden by a cloud of dust, and it talks to us through X-rays and radio waves. Priests, doctors, and artists would all say, "Is this a god? A threat? A dying giant ready to blow up?" Technologically, you'd have evolved under this shadow. Your telescopes, designed to pierce dust, would be exceptional. Infrared astronomy would be your first language. You might detect the slow collapse of the star in real time, centuries or even millennia before the final death knell, watching as light curves and stutters around the enveloped core. Perhaps you'd even send probes into the cloud, risking their annihilation for one more piece of data. Even when the behemoth star finally dies, like when it goes supernova or hypernova, there won't be a lot of light. Instead, there will be too much difference. Your umbra would turn into a huge energy wave that would blind you. What was just a shadow would get brighter and brighter until it reached the sky. It wouldn't be safe to live in the light-year shade of the behemoth star. It wouldn't be calm. But people would never forget it. You would be a society that was shaped by being close to the universe's biggest star, a family raised by a giant. The final flash, supernova or hypernova. It will not be a quiet end for the behemoth star. The fire in the hearts of stars is what makes them live or die. When the fire goes out, gravity takes over, which is very bad for supergiants like the behemoth star. But not every star death is the same. Some stars drift off into the night. Some, like the behemoth star, explode so powerfully that the sound can be heard across worlds. The question isn't if the behemoth star will die or not. When it finally ends, it will either be a supernova or a hypernova, which is even scarier. The question is how violently it will do so. There is already a lot of information about how strong supernovae are. It happens when a very large star runs out of nuclear fuel. Without fusion to push outward pressure, the star's center falls apart in a very short time due to its own gravity. This quick collapse sends shock waves outward that destroy the star's outer layers, releasing more energy than the Sun will ever have in its 10 billion year lifetime. For a star the size of the behemoth star, 1,500 times the Sun's radius, the scale is nearly unimaginable. If it dies as a Type II supernova, the explosion would outshine its entire host galaxy for a short time. That's more light than billions of stars combined. The blast wave would travel through the surrounding dust envelope and interstellar space at thousands of kilometers per second, tearing apart everything in its path, compressing gas clouds, and possibly triggering new waves of star formation in distant systems. But the behemoth star might go on to something else. Because it has lost so much mass, is very bright, and is so big, it is a good option for a hypernova, which is an even rarer and stronger type of explosion. A hypernova is 100 times more powerful than a regular explosion. Long-duration gamma-ray bursts are beams of radiation so strong that they could destroy planets across light years if they were pointed directly at them. They are linked to the birth of stellar mass black holes. If the behemoth star goes hypernova, it will release a burst of energy equal to 10 circumflex 45 joules. That's the same amount of energy that the Sun gives off over 10 billion years, but in less than a minute. The flash would be visible from the farthest reaches of space. The blast that would follow would clear hundreds of light years of space of cosmic dust, changing the shape of the part of the Large Magellanic Cloud where the star is located. Astronomers on Earth, or on any world watching from a safe distance, would witness a spectacle not seen in recorded history, a cosmic fireworks finale that marks the end of a giant. In fact, some scientists speculate that if the behemoth star exploded today, its light might already be on the way, a ghost message from a star already gone. What comes next? Depending on how much mass is left over after the explosion, the core that falls apart could either become a neutron star or a black hole. A neutron star is so dense that a teaspoon of its matter weighs billions of tons. If a black hole is born, it might have a mass and spin that go against what we know about physics. This is especially true if the behemoth star had a partner star that gave it rotational momentum. Gamma-ray bursts and the cosmic death beam. A gamma-ray burst, or GRB, is the most dangerous thing that could happen in the universe if the last few seconds of the behemoth star end in a hypernova. These bursts last only a second or two, but are unbelievably strong. If one happened in our galaxy and was aimed straight at Earth, it would be able to remove our atmosphere in seconds and wipe out all life on Earth. Gamma-ray bursts are not explosions in the traditional sense. They are focused beams of pure energy launched at near light speed in two opposite directions from a collapsing star. They occur when the star's core collapses into a black hole, and angular momentum, combined with magnetic fields, channels the collapsing material into twin relativistic jets that pierce through the dying star's body and shoot into space like cosmic sniper fire. These bursts last anywhere from milliseconds to several minutes. In that short span, they can release more energy than the sun will produce in its entire lifetime. The reason for their intensity is the concentration, focused energy like a death laser, rather than the spherical detonation of a typical supernova. A red supergiant, with a size nearly 1,500 times that of the Sun, with a massive, unstable envelope of gas and dust. If it collapses directly into a black hole and channels its final fury into a GRB, the result would be a beam stretching across galaxies, potentially visible billions of light-years away. We don't yet know if red supergiants like the behemoth star can produce long-duration gamma-ray bursts. Most known GRBs come from stripped envelope stars, massive stars that have shed their outer hydrogen layers, often becoming Wolf-Rayet stars. The behemoth star still has a significant hydrogen envelope, which might choke the jet before it escapes. However, recent studies suggest that if the star is rotating fast enough, and if magnetic fields are strong and well aligned, a GRB could still burst through the envelope. If it did happen, it would start with a flash of high-energy gamma radiation that can't be seen by humans but is deadly to living things. If the beam hit a world, it would remove the ozone from the air, expose a lot of people to radiation, and cause the world's ecosystem to fail. The behemoth star is safe because it lives in the Large Magellanic Cloud, which is more than 160,000 light-years away. Even if it sent a GRB straight at Earth, it probably wouldn't be strong enough to kill us. Still, even from that safe distance, seeing such an event would be a once-in-a-civilization chance for scientists. Waves of data would fill the radio spectrum. Telescopes that use infrared, X-ray, optical and radio waves could pick up the afterglow, which is the glow that lasts long after the main burst. This would let scientists see how star titans die, fall apart, and turn into black holes in a way that has never been done before. Perhaps gamma-ray bursts might shape the evolution of life across the universe. Some theories suggest they've already wiped out life on Earth at least once, possibly triggering the Ordovician extinction 450 million years ago. If so, then GRBs aren't just stellar death beams. They are cosmic gardeners, pruning branches of life across galaxies, clearing the way for new ecosystems to rise. From Titan to remnant, neutron star or black hole. A star doesn't just disappear when it dies, it leaves something behind, a last form, signed by. The death of a stellar giant like the behemoth star isn't just exciting, it's what global change looks like. What does the end of a monster like that look like? What's left after the last fire? There are two main types of stars that could be the behemoth star, neutron stars or black holes. Both are strange, mysterious and extreme, but they show very different ways that stars die. It is very important for scientists to know which direction the behemoth star will take in order to learn more about this star and the life cycles of all massive stars in the universe. Let's start with the neutron star. These are the densest known objects that don't collapse into black holes. Imagine the mass of the Sun, squeezed into a sphere the size of a city. A single teaspoon of neutron star material would weigh as much as a mountain. These remnants are made almost entirely of neutrons, packed so tightly together that atomic structures cease to exist. If the behemoth star ended up as a neutron star, it would mean that the star had enough mass to collapse its core, but not so much that gravity could overcome the pressure created by the neutrons themselves. That pressure, called neutron degeneracy pressure, is what holds the remnant up against the crushing pull of gravity, but the behemoth star might be too big for that to happen. With a diameter more than 1,500 times that of the Sun and a dusty envelope that could hold several solar masses of material that has been thrown out, the behemoth star may very well collapse into a black hole. A black hole is a singularity, which is a point of infinite density surrounding by an event horizon from which nothing, not even light, can escape. This is where things start to go wrong. As a black hole, the behemoth star will be one of only a few things that can change reality itself. It also wouldn't be a normal black hole. If it holds on to a lot of mass when it collapses, it might turn into a stellar mass black hole or even a primordial intermediate mass black hole, which is a very rare and badly understood type of object. What makes a difference is how much mass is lost before the box falls apart. Through its star winds and dust environment, the behemoth star is already losing huge amounts of matter. A neutron star might still be possible, but it is not likely if enough of that mass is thrown out before the core falls apart. But if there is still too much mass, there is no way back. The weight of the star's core will pull it into a deep hole from which not even information can be found. The moment of failure would be terrible. The core would collapse in milliseconds, releasing more energy in that 1 second than the Sun does in its whole 10 billion year life. As the shockwave spreads, it creates a supernova, or a hypernova if the collapse is strong enough, which is one of the most powerful events in the universe. Either a magnetic neutron star spinning hundreds of times per second, or a new black hole hiding in the debris would be left behind. Because the behemoth star is over 160,000 light-years away, we're seeing it as it was when giant mammoths walked the Earth. We might never see it happen in real time. We will be able to see its end fate one day, maybe tomorrow, or 1,000,000 years from now. Stardust legacy, seeding the universe with elements. The death of a massive star like the behemoth star is not an ending, it's a beginning in disguise. While we often marvel at the size and spectacle of these giants, their true legacy is quieter, invisible, and absolutely fundamental to everything we are. Every atom of calcium in your bones, every bit of iron in your blood, every molecule of oxygen you breathe, was forged in the heart of a dying star. Nucleosynthesis is the name of this process, and it's like the world's biggest magic trick. Things that are lighter become heavier as a star grows. The first thing to fuse is hydrogen. Next come helium, carbon, oxygen, neon, magnesium, and silicon. In a supernova or hypernova explosion, on the other hand, the rarest and strongest elements are made in a minute or two. U-235, platinum, and gold are these. As the core finally breaks apart, shockwaves are sent out into space that smash atoms together so hard that they make new elements. When the behemoth star is over, it will change into one of these space forges. It'll launch billions of tons of stuff into space, which will fill up the area between the stars. Things like these will keep moving for a very long time because of gravity and the winds of stars. In the end, they will be used to make new planets, moons, stars, and living things. It's poetic. The very act of dying gives birth to new potential. And it's not just theory. We've seen the evidence. Supernova remnants like the Crab Nebula or Cassiopeia A reveal stunning clouds of expelled stellar material. These clouds glow in every wavelength. X-rays, ultraviolet, visible light, each hue revealing a different element scattered into the void. Over time, this matter clumps, cools, and begins the cycle anew. It's also a timeline. Our own solar system was born from the ashes of stars that came before. The Sun is a second or third generation star, formed in a nebula enriched by supernovae. The Earth, the planets, even the water in our oceans. They all contain elements that once burned in stars now long gone. The behemoth star's destiny, then, is to seed the future. Its atoms will become part of stars not yet born, in galaxies not yet formed, around planets we may never see. It is a single act in a chain reaction stretching back to the dawn of time and forward to the heat death of the cosmos. To understand the terrifying power of the biggest stars is also to understand our place in the universe. We are not separate from them. We are not distant observers. Supernova remnants, nebulae of the gods. A big star like the behemoth star doesn't just disappear into thin air when it dies. It explodes fiercely, wildly, and magnificently, sending shock waves across the galaxy and carving a work of art out of light and color into the void. It doesn't leave behind a grave, but a monument, part of a supernova. These are the nebulae of the gods. They are huge, painted in light-emitting pieces of dead stars. A supernova residue is what's left over after a disaster. The explosion sends the star's outer layers flying off at up to 30,000 kilometers per second. This makes a bubble of charged gas and dust that can reach hundreds of light-years away. There may be a neutron star or black hole at the center, but the galaxy around it is what draws our attention and inspires our creativity. These pieces are found in many places. Some, like the Veil Nebula, shine in ultraviolet and X-ray light like torn silk. Some, like Tycho's supernova remnant, are surprisingly round and grow outward in perfect deadly order. Chinese scientists saw the Crab Nebula form from a supernova in 1054. It is still growing, with its ionized gas strands making a kaleidoscope of color and swirling motion. Not only are these buildings beautiful, they are also very important. Scientists can learn a lot from the remains of supernovae. Their light sends data about the elements that were made in the blast, like iron, nickel, cobalt, and more. Their shapes show us how the star that burst was not balanced inside. Their energy affects gas clouds nearby, which starts the formation of new stars. In this way, the death of a star directly leads to the birth of new stars, keeping the big circle going. Astronomers should be able to see the supernova residue from the behemoth star. It is likely to be one of the biggest and most exciting ever seen. Since the behemoth star is in the Large Magellanic Cloud, which is far from our galaxy but close enough to watch in detail, its death would give us a new way to look at how ultra-massive stars explode. Many types of light, from X-rays to radio waves, would be able to see its remains for tens of thousands of years. Each type of light would tell a different part of the story. The dust and gas would finally mix with the material between the stars, creating new stars, worlds, and maybe even life. We tend to think of death as an end, but in astronomy, it's often the opposite. Supernova remnants are the fingerprints of creation, scattered across the galaxy, reminding us that from destruction comes new order. These divine nebulae are not just reminders of power, they are promises of what comes next. The role of giant stars in galactic evolution. When we look up at night, we usually notice the stars, those bright points, the constellations, and the planets that move around them. But the truth is that stars are more than just pretty things in space. They bring about change and form galaxies. This is especially true for the huge stars like the behemoth star. Their scary strength isn't just a show of how strong the universe is. It's a key part of how galaxies live and die. Massive stars aren't very common, but when they do happen, they have a huge effect. Even though they don't live long, sometimes only a few million years, everything around them is changed by them. As soon as these stars light up, they start changing the world around them. Their strong radiation ionizes the gas around them, and their strong stellar winds cut out cosmic holes in molecular clouds, spreading gas and starting new rounds of star formation. In their final moments, giant stars undergo the most influential event of their existence: supernova explosions. These aren't just fireworks, they're chemical engines. The explosion seeds the galaxy with heavy elements forged in the star's core: carbon, oxygen, silicon, iron, even gold. These are the elements that make up planets, plants, animals, and you. Without massive stars, galaxies would remain primitive, devoid of complexity. The early universe consisted almost entirely of hydrogen and helium. It was only through generations of massive stars living and dying that the universe became chemically rich enough to support life. This metal enrichment is fundamental to the evolution of galaxies. Each giant star acts like a stellar alchemist, transforming the simple into the complex. But these giants also control galactic feedback mechanisms. When massive stars explode, they push energy into the galactic medium, heating and stirring gas clouds. This feedback can halt star formation by dispersing gas, or paradoxically, trigger new waves of stellar birth in shock-compressed regions. In this way, massive stars are both destroyers and creators, regulating the rate at which galaxies grow and evolve. The behemoth star, with its immense size and extreme mass loss rate, is already affecting its surroundings. The dust envelope it has shed carries material into the Large Magellanic Cloud. In time, it will explode, sending shock waves through the interstellar medium, lighting up the cosmic neighborhood, and sculpting its galactic environment with explosive artistry. Also, let's not forget what this means for gravity. If the behemoth star falls into a black hole, it will bend space-time and may merge with other compact objects in the future. This could create gravitational waves, which are like cosmic sounds that travel through the universe and give astronomers on Earth important information. How we discovered the behemoth star, the history of observation. Before it was known as the huge celestial object we admire today, the behemoth star was just a strange dot in the sky in a faraway place. It was a weak source of infrared radiation deep in the Large Magellanic Cloud. Like many other big discoveries in astronomy, it wasn't amazing pictures that led to the finding. Instead, it was data, patience, and a camera directed in the right direction. The first collection of the behemoth star was made by Westerlund, Olander, and Hedin in the 1970s. This is where the WOH in its name comes from. At the time, the star didn't make anyone look twice right away. A lot of bright, dusty red supergiants live in the Large Magellanic Cloud. But as optical and photometric methods got better, scientists saw that this wasn't any red supergiant. It was one that behaved in ways that were not consistent with what was known about stars. The turning point came with the advent of infrared astronomy. Visible light can't penetrate the thick dust envelope surrounding the behemoth star, but infrared waves can. Observations using instruments like the Very Large Telescope, VLT, and the Spitzer Space Telescope began to reveal startling data. The star's light was being heavily reprocessed by dust, indicating massive material loss. The volume of expelled matter and the star's luminosity suggested something extraordinary. In 2007, a detailed study of its surrounding dust envelope using high-resolution interferometry confirmed what many had suspected. The behemoth star was potentially the largest star ever discovered. With an estimated radius over 1,500 times that of the Sun, it earned its place in the Cosmic Hall of Fame. Nevertheless, it wasn't easy to figure out the behemoth star's actual size. Astronomers had to use models to figure out what the star was really like, because it was surrounded by a thick shell of gas and dust. These models took into account how light is absorbed, scattered, and re-emitted. They solved a cosmic investigative puzzle that could only be done with data from multiple wavelengths. The work is still going on. As technology gets better, we learn more about this star. For example, the James Webb Space Telescope could help make it smaller, more stable, and made of better materials in the future. Infrared sensors will get better over the next 10 years, and it will be possible to see through thick cosmic clouds. This will allow for a more complete map of the behemoth star's surroundings and how it works on the inside. But beyond the data lies a deeper truth. The discovery of the behemoth star is a testament to human curiosity. From faint signal to cosmic legend, It's the story of how observation, persistence, and imagination allow us to uncover giants in the sky. In that sense, the behemoth star isn't just a discovery, it's a monument to what our minds can grasp when we dare to look beyond the visible. Tools of the hunt: telescopes, spectroscopes, and infrared eyes. The story of the behemoth star is not just a tale of celestial proportions, it's also a celebration of the tools that made such a discovery possible. Unveiling the mysteries of a star cloaked in dust, radiating more than 280,000 times the luminosity of the Sun, and hidden away in a neighboring galaxy demands more than just a telescope. It requires a symphony of observational techniques, spectral analysis, and cutting-edge instruments that can peer through cosmic veils. The earliest observations of the behemoth star relied on ground-based optical telescopes, which first recorded the star's photometric irregularities. But these telescopes were limited in what they could detect. The behemoth star, enshrouded in a thick torus of gas and dust, appeared faint and ambiguous when viewed in the visible spectrum. The light that did reach Earth was already distorted and diminished. Because its bands are longer than those of visible light, infrared light can pass through dust that usually blocks out faint or dead stars. The European Southern Observatory, ESO, runs the Very Large Telescope, VLT, in Chile, which gives one of the best views of the behemoth star's dusty environment. Scientists used high-resolution imaging and analysis to separate the star's radiation, study the dust's makeup, and figure out that it was losing mass at one of the fastest rates ever seen in a red supergiant. But Earth's atmosphere blocks a lot of the infrared spectrum, so even infrared telescopes that are on the ground can only see so far. In come telescopes that are in space, such as the Hubble Space Telescope and the Spitzer Space Telescope run by NASA. Spitzer in particular helped scientists make models of the behemoth star's structure, such as its large dust shell and how the temperature inside it was distributed. It helped lay the groundwork for knowing how bright this star is and how huge it is. The spectroscope, a machine that splits incoming light into its different colors, was also very important in the search. Scientists could read the chemical marks left by the atmosphere of the star with this. The spectrum of the behemoth star showed that it had heavy elements that were made deep inside it and then pushed out into the nearby dust. These lines in the spectrum showed that there was internal fusion, convection instability, and a star nearing the end of its life. Astronomers also used interferometry, a method that mixes light from several cameras to make it look like there is a much larger aperture, which makes the clarity much better. Researchers used tools like the VLTI, Very Large Telescope Interferometer, to clear up the star's dust shell structure and prove its toroidal shape. This helped them make better predictions about the star's size and behavior. Now, with the James Webb Space Telescope in operation, the next phase of observation begins. With unprecedented infrared sensitivity, JWST can peer even deeper into the behemoth star's dusty cocoon, perhaps revealing more details about its core, its pulsation behavior, and whether a hidden companion star lurks nearby. The case of the behemoth star is proof that cosmic discovery isn't just about looking. It's about knowing how to look. It's about having the right tools in the right hands and the patience to interpret faint whispers from the stars. The telescopes and instruments we use are not just extensions of our eyes. They're extensions of our curiosity. The biggest star and the future of stellar physics. The behemoth star isn't just an interesting piece of astronomy, it's a challenge to current star physics that it needs to answer. Scientists have had to rethink what they thought they knew about how stars form, change, and die because of this one star, a red supergiant that is covered in dust and hidden in the Large Magellanic Cloud. Why? Because a star this big shouldn't exist by any normal standards. Still, it does. The mass loss rate of the behemoth star is so high that it's almost ripping itself apart. It goes beyond the Hayashi limit and is on the edge of gravity instability. Its huge dusty torus, which was probably made by this fast-moving debris loss, points to internal processes or partner interactions that we don't fully understand yet. There is a kind of stellar grey zone around it, where what we've modelled and what nature has actually made meet. This has huge implications for the field. For one, massive star evolution models, particularly those that simulate the red supergiant phase, are now under renewed scrutiny. The behemoth star defies expected limits on radius, luminosity, and density profiles. Our current equations for stellar structure, particularly those used to predict how stars move through the Hertzsprung-Russell diagram, may need to be revised for cases this extreme. If the behemoth star is not an anomaly, but rather the first of a broader class of extreme red supergiants, then entire swathes of astrophysical theory may be missing critical ingredients. Another potential implication involves binary star systems. If future observations confirm that the behemoth star has a companion, possibly a blue main sequence star, it could lend further support to the idea that binary interactions dramatically alter stellar evolution. This would align with a growing body of research suggesting that a large percentage of supernova progenitors are part of binary systems, their fates intertwined by tidal forces, mass transfer, and angular momentum exchange. There's also the question of dust production in galaxies. Massive stars like the behemoth star contribute heavily to the dust budget of the universe, especially in galaxies with high star formation rates. But the amount of dust being ejected from the behemoth star is unusually high, more than what standard models predicted for red supergiants. This means such stars may play a more dominant role in seeding galaxies with dust and heavy elements than we've previously appreciated. For early galaxies especially, this could change how we understand the enrichment of the interstellar medium. Studying stars like the behemoth star helps us prepare for the future, not just of this star, but of our Sun and others like it. While the Sun will never become a red supergiant, many more massive stars in our cosmic neighborhood are headed in that direction. Observing the behemoth star is like watching the endgame of a massive star's life in real time, giving us a window into the mechanics that will eventually lead to supernovae, neutron stars, or black holes. What we think of as a star might change after seeing the behemoth star. It might be hard to tell the difference between a star and a cloud, or between fusion and collapse, when it is very swollen and disorganized. This makes us sharpen our language and rethink our categories, kind of like how Pluto's position as a planet changed as new information came in. New telescopes like the Extremely Large Telescope, ELT, and the James Webb Space Telescope are pushing the limits of how sharp and sensitive they can be. Soon, stars like the behemoth star will no longer be hidden secrets. They will be case studies that show how a new area of star astronomy works. Why giant stars remind us how small we truly are. These are the shocking numbers. 1,540 times the size of the Sun, a cloud of dust that is over a light-year long, something that is more than 280,000 times brighter than our star. The behemoth star doesn't just break records. It also serves as a warning, something to remind us of how big, strange, and humbling the universe can be. The Sun is often thought of as very big, and it is to us. Our solar system is held together by its gravity, and it's the star that powers life on Earth. Still, the behemoth star makes it seem very small. If you stood on a made-up world that circled this monster, you wouldn't see a sun, you'd see a sky full of sun. A fiery red screen that goes from horizon to horizon and floods your world with constant, scorching sunlight. You wouldn't just watch the sky burn, you'd watch the sunset. And yet, in the face of this cosmic titan, our planet keeps spinning. Our lives go on, measured in hours and heartbeats, utterly unaware of the celestial extremes unfolding far beyond our skies. The behemoth star is 168,000 light-years away, and yet its light, faint though it is, has crossed the void to tell us a story about power, fragility, and the fleeting nature of all things, even stars. Because here's the truth. Even the biggest stars die. The behemoth star will eventually fall apart, no matter how big or angry it is. It will no longer be visible in the night sky, and it will go away with a bang. It could go supernova, send gamma-ray bursts hurtling through space, or fall apart into a black hole that eats up all light and time. And then there will only be dust, or stardust, left over. This is where new worlds, stars, and maybe even life will begin. That's what amazes people about stars like the behemoth star. They serve as symbols of both size and history. We are small, but our very atoms were formed in stars like this one. The carbon in your breath, the iron in your blood, and the calcium in your bones were all made in a fiery place in space billions of years before you took your first step. Even after we're gone, stars like the behemoth star will keep the cycle going by dying, falling, and spreading the building blocks for new life. We are, as Carl Sagan said, a way for the universe to know itself. And in learning about the behemoth star, we don't just learn about distant stars. We learn about ourselves, our past, our future, our place in a story written across the sky. The behemoth star is a monument to the universe's wildest possibilities. It is a fire-breathing monster covered in dust that is about to fall apart but shines with a light that is brighter than many solar systems. We don't just learn about stars when we study it. We also learn about the limits of life, where elements come from, and the strange rules that guide the biggest stars in the universe. We're not just looking out as we learn more about these huge stars. We're also looking back into the fire of creation. Don't forget to like, share, and follow if this journey amazed or interested you. There's more magic out there in the stars.